Hello everyone, today I'll be going over the long-awaited Spacetime Algebra. This is a video that I've been looking forward to making for a very long time, so I'm really excited that I'll be able to present it to you guys today. Now, a bit of a disclaimer: in order to understand this video, you need to have taken an intro to quantum mechanics course and know what vector spaces are. You also need a little bit of relativity knowledge, but other than that, this video will be sort of self-contained. So don't procrastinate. Let's start. The spacetime algebra is defined as a vector space with basis gamma naught, gamma 1, gamma 2, gamma 3, where gamma mu are the gamma matrices. Now, it's perfectly fine if you don't understand what I said at all. I'll be going over it in like 5 minutes. Now, these gamma matrices obey this commutation relation over here, known as the Dirac Commutator. And these gamma matrices also show up in the Dirac Equation. Now, in this video, I will be deriving the Dirac Equation from the Klein equation. Then, I'll be defining the Dirac Commutator, and after that, build algebras from gamma mu, and finally connect it to space-time. So let's start. The Klein-Gordon equation is this. Now, first of all, a bit of notation. By partial mu, where one is an upwards index and the other is the downwards index, I really mean partial mu, Minkowski metric mu nu, partial mu, where the Minkowski metric is this metric over here, where the first input is 1, and everything else is -1 on the diagonal, and everything else is 0. So partial mu will just be partial not, minus partial 1, minus partial 2, minus partial 3. We have a minus over here due to the minus signature in the diagonal, and 1 over here to make it unity. So that's just the notation that we're using today, and yeah. Also, partial mu is just defined as partial over partial u nu, where u naught equals t, u1 equals x, u2 equals y, and u3 equals z. Just a shorter way of writing it. So now that you got the notation down, let's actually talk about this equation. Now here, of course, is the Klein-Gordon equation, and it has a couple of problems. Let's just write it down again for space. Looks like my Apple Pen died. Just wait like 2 seconds. 1, 2. Okay, so there are a couple of problems with this Klein-Gordon equation. Oh, and first of all, how do we derive this equation? Well, we take the Einstein energy momentum relation, and what we do is we substitute E for the Hamiltonian operator, and we substitute P for the momentum operator, and from there you can derive this equation shown here. I'm not going to walk through the derivation, but that's just how you do it. So yeah, there are a couple of problems with the Klein-Gordon equation. One is that it yields negative probability densities. And 2, it's second order in time. And it turns out that being second order in time is actually what causes these negative probability densities. So if we can make this equation only first order in time, we can make the negative unphysical densities go away. So how can we take this Klein-Gordon equation and make it second order in time? How do we go about that? Well, one way is to kind of factor out this equation into two parts. So where each part is first order in time, and then declare one part its own wave equation. Now, that may seem a bit abstract to you, but it's fine. I'll be going over how we actually do this. So, again, the main idea here is to factor out this equation. Now, I'm going to rewrite this equation in a bit of a different way. Oops, my Apple Pen died again. Probably should have charged it before doing this video. Okay. So we're just gonna rewrite this equation in a bit of a different way. I'm just gonna sigh. Okay. So what we want to do is just take this part and kind of factor it into two parts. So how can we do that? Well, one way is to take the square root of gamma of partial mu. And remember, partial mu is just partial not plus partial 1 plus partial 2. Sorry, partial 2 minus partial 3. Partial 3, these should all be minuses. But this won't, but if we do this, we can't really go any further from there. Since, like, if we have a sum or a negative sum under a square root sign, we can't simplify any more from there. So we've kind of reached a dead end. But maybe there's some loophole, some way around this. What if we just assume that the square root of partial not minus partial 1 minus partial 2 minus partial 3 could be written as some linear combination of partial not plus gamma 1 partial 1 plus gamma 2 partial 2 plus gamma 3 partial 3. So we're just assuming, we're just making a guess here, an ansatz kind of, that the square root of this term can be written. Oops, my bad. There should just be one term here. So we're just assuming that the square root can be written as, here, let me just write it again. I made a mistake the first time. So we're assuming that the square root of this can be written as a linear combination of the individual partial terms. Okay? That's all we're doing. So here we have partial not, partial 1, partial 2, and partial 3. And we're assuming that the square root of it squared is just going to be a linear combination of the individual terms scaled by some factor of these, scaled by these gamma numbers. These gamma numbers may be scalars, they may be matrices, they may be quaternions, who knows what they may be. But we're just assuming that it's going to be a linear combination of the partial numbers. Okay? Now, let's actually have to ignore this over here. This is some future stuff. Okay. So, he basically said that partial, or the square root of partial mu is essentially gamma mu partial mu. Okay? Where this is just like a true linear combination. There's no Minkowski metric hidden there. So this, of course, implies that partial mu would then be would then be gamma nu, partial mu. Or in other words, if this equals that, then this squared, which is just this by itself, should be this expression, this entire expression squared, if that makes sense. Or to put it more explicitly, we're saying that partial not minus partial 1 minus partial 2 minus partial 3 equals gamma not partial plus gamma 1 partial plus gamma 2 partial plus gamma 3 partial squared. And that's what we're saying. So we have to make these two expressions equal. Now when we square this term over here, we get this. So you just get this when you square this expression over here. Try it yourself. So this has to be equal to partial not minus partial 1, maybe just partial not minus partial 1 minus partial 2 minus partial 3 partial 3. And we actually see partial not right over here. And we see partial 1 right over here. And we see partial 2 right over here. And we see partial 3 right over here. So we want to equate them to terms that already exists in the sum, which implies that this would have to be 1. This should be 1, and this should be 1, and this should be 1. Since these should be minus 1 actually. My bad. Since there's like an invisible hidden 1 in front of partial not, and there are minus 1s ahead of the other terms. So we've just deduced that partial not should equal 1, and gamma 1 should equal gamma 2, which should equal gamma 3, which should equal minus 1. Now what about every other term? Now there are a number of ways to go about this, because every term, everything in between should all add up to be 0, right? Since there's like no other term here, or you could say that there's a 0 here, and this 0 should equal all the other terms added up together. So there's two ways to go about this, or a number of ways. We could declare that partial nu equals to Klein delta mu, or really just equals 0, right? Equals 0 if if mu does not equal to mu. But this isn't a very good way, because it's not as useful for us, since it makes that term become 0, right? And just solely 0. So we want a way that gives us a bit more freedom with these gamma numbers, if that makes sense. So the other way to make all of them add up to be 0 is to declare that gamma nu equals minus gamma mu for mu does not equal to nu. This is an ingenious way, right? Since, for example, gamma is what did I just do? Since like gamma 1, gamma 3 would equal minus gamma 3, gamma 1, right? So and here we'd have gamma 1, gamma 3, which is like right over here. So I'll cross cancel out with gamma 3, gamma 1. So both terms would go away, and they'd add up to 0. And that would happen for every other terms of every gamma mu has a corresponding gamma mu, where gamma mu does not equals to gamma mu, and they cancel out with each other, which makes all the other terms come out to be 0. So yeah, that's a way, and that's the way that we're gonna use to make all the other terms cancel out. So what we have are the 3 golden rules of these gamma numbers. We found that gamma naught should be 1. Gamma 1 should be equal to this, which equals -1, and gamma mu should equal minus gamma mu. And these are the 3 rules that the gamma matrices ought to obey to make logical sense. Now, there is actually a way to combine these 3 statements into like one equation, kind of, and that's the Dirac Commutator. You can take the commutator of gamma nu, that equals gamma nu plus gamma mu by definition, which equals 2 times the Minkowski metric mu nu, where the Minkowski metric mu nu equals 1 if mu equals nu equals 0, minus 1 if mu equals mu and does not equal 0, and 0 if mu does not equal to nu. Now, how does this commutation relation tell us these 3 statements? Well, just think about it. If we have mu equals nu equals 0, we have the commutator of gamma naught equals gamma naught plus gamma naught, which equals 2 times Minkowski metric naught, which is just 1, right? Which implies that these would both have to be 1, which is what this says over here. If mu does equal to nu but does not equal to 1, well, then we have commutator of gamma nu equals twice the Minkowski metric mu nu, which is just going to be -1 for mu equals nu and does not equal to 1, which implies that gamma nu, sorry, and it implies that these would be the same, right? So it's essentially this, right? So it would imply that gamma mu plus gamma mu should equal 2, right? So it equal -2, which means that each term should be -1, which is what we get over here. And of course, when mu does not equal to nu, it would imply that gamma mu nu equals minus gamma nu mu. You can check this out for yourself. This commutator is pretty powerful and pretty strong because it tells us everything we want to know about these gamma number relations. Okay? And it's actually what I showed at the start. So if you're following along, you now know what that... It's this over here. So if you're following at the start, now you know what that equation, this commutation relation means. It's called the Dirac Commutator. Okay, nice. That's cool. But we still don't know what these gamma numbers are. I mean, I said that they were matrices at the start, but just forget that I said that. We don't know what these numbers are. So we've reached a problem, right? But there's no need to worry here. Because, oops, I just spoiled it for you guys, but there's no need to worry here. Because we can kind of deduce what these gamma numbers may be. Right? Because by looking at their relations, we can kind of guess what numbers they might be. Because note that gamma nu equals minus gamma nu for mu does not equal to nu, right? So they anti-commute under multiplication. What other things in math do we know that anti-commute under multiplication? Matrices, right? So Dirac, when he was doing this, like he was like, oh wow, these things anti-commute. Well, also anti-commute matrices. So he just guessed that these gamma numbers were matrices, and he found out what matrix input values they'd have to be for this commutation relation to actually hold, which is this. This is what each gamma number ought to be for the commutation relation to actually hold properly. So yeah, I'm not sure how he actually found these specific matrices. I guess maybe he just guessed and checked. Maybe there's a method or algorithm that he used, but that's what these matrices turn out to be. Okay, so that's really cool. So we know what these matrices are, but yeah, let's go back to our word list. So yeah, oops, we haven't did number 1 yet. Okay, yeah, so let's derive the Dirac equation finally. So let's check back with our Klein-Gordon equation. All right. Now we remember that we found that that these partials are just gamma nu, partial mu. So you're gonna separate that, or just plug that in. Gamma nu, partial mu. So plus m squared psi equals 0. Okay. Now what's next? Well, we have two squares here, right? This is like a square, and this is a square because like it's gamma mu partial mu squared. So you can treat this plus sign as like minus negative m squared, since minus is just a positive. And then we can treat it as a difference of two squares. And we know from Algebra 1, the distance of two squares, we can factor that into like two terms. So we can factor this out into I gamma mu partial mu minus m times I gamma nu partial nu plus m psi equals 0. So we just use difference of two squares to factor this out. And remember, we originally wanted to factor that into two terms, and we just have done that. So there are two ways. There are two options here. We can let psi go to this term, I gamma mu partial mu minus m, and set that equal to 0. Or we can set I to these to the new terms and set that equal to 0. So either way is just convention. You get the same result, but historically, for whatever reasons, we usually choose this solution. So and note that this is actually first order in time, right? Since there's no longer partial mu, there's just one partial there, right? Okay. So we're almost done here. We're almost done. Now we can define partial or gamma mu partial mu. We can define that as this partial slash called the Feynman slash notation to get I partial slash minus m psi equals 0, and you finally derive the amazing, spectacular, fantastic Dirac equation. Yay! We can clap for ourselves. Give like a yay there. But yeah, that's the equation. Now, what does this equation actually describe? Well, note that gamma mu are matrices, right? So we'd have like I times like some gamma matrix, like gamma not gamma 0, 1, gamma 0, 2, and so on, right? Times partial mu minus m psi equals 0. But there's a problem here, a big problem. Because we have a matrix and we're subtracting it by some constant, right? And getting 0. We can't do that. We can't add matrices to scalars or vectors to scalars for the matter. So we have to reinterpret a couple of these signs here. So you have to reinterpret gamma partial mu to be some 4 vector. Partial naught, partial 1, partial 2, and partial 3. So here we'd have times partial, not partial 1, partial 2, partial 3, to make the calculations actually work out. And we have to reinterpret the mass as well, kind of. We can't really say that mass is just some 4 mass vector, right? Since like mass is just a constant, right? There's no like components to mass. That doesn't make any sense. So the alternate route is to instead let mass be a constant, but just change mass to mass times the identity matrix to have M0, 0, M. So instead, we can just multiply mass by the identity matrix so that we have a matrix here. And that, all of that times psi should equal 0. Well, we're multiplying it by psi, which is a constant, right? So again, there's a problem. So instead, we have to reinterpret psi to not be a scalar field like the Klein-Gordon equation, but a vector, the vector field. So you have psi naught, psi 1, psi 2, psi 3 instead. And then 0 would be the 0 vector. So something pretty subtle but very profound has occurred here. We found that psi is no longer a scalar field, but some vector, kind of. And the particular vector that psi is a spinor. Psi is actually a spinor. Excuse the noise, I'm with some other people here. But, yeah, psi is a spinor. And the kind of spinor is called a Dirac spinor, because it's in the Dirac equation, right? So, yeah. So why exactly is psi a spinor? Well, it makes sense how it's a vector, but why specifically a spinor? Well, my guess, like I don't really know, but my guess is that because psi requires one SU2 or Lorentz matrix to properly rotate, which spinors spinors only need one SU2 rotation. Another guess is that it's because the spinor rate is psi 1, psi 2, psi 3. That actually equals, when you put a basis for spin states, that comes out to be psi naught spin up plus psi 1 spin down plus psi 2 spin up plus psi 3 spin down. And the first two terms describe matter. The latter two terms describe something called antimatter, which is like negative energy, kind of. And yeah, that's why it's called a spinor. But that's only for some particular representation for the Dirac spinors. So that isn't the general reason as to why. But my guess is that it's because it rotates with an one SU2 matrix. And you can go to my SU2 video. It's called Spinning Spinors. I talk a bit more about like the rotations of spinors, how you properly rotate them. So yeah, I know if you got a type of off track, but yeah, psi spinor. It's sometimes called a bi-spinor because the spinor, the spinors usually have like two components, right? So you have 4 components, which is 2 times 2, so we call it a bi-spinor. So yeah, psi is a spinor. So you have just successfully derived the Dirac equation from the Klein-Gordon equation, which is relativistic. And it actually describes only spin 1/2 particles as well. And we have also defined the Dirac Commutator. Now we have to build algebras from gamma mu. Okay, this is a very cool part. This is the core part of this video. So, let's take a sidetrack here and just talk about complex numbers. So, we have I squared equals -1. How do we solve for I? Now, there are 2 ways to go about this. We can declare I to be a matrix, where I equals matrix 0, -1, 1, 0, and 1 to be the identity matrix. And that would actually solve the equation. You can try it out yourself. It actually solves the equation here. Or you could declare I to be its own new number. And I squared equals -1 by definition. And the properties of this new I number are that the dot product, I guess you could say, of I with itself is -1. Okay, now we can also do something similar to this with these gamma matrices. So we had these, if you remember from earlier, like 2 seconds ago, we had the Dirac Commutator, the commutation of relations. Let's say that gamma naught should be 1, gamma 1 should equal gamma 2 should equal gamma 3, which should equal to -1. And we had that gamma mu should equal minus gamma mu should equal 0 if mu, and it's like, I honestly don't know why it's convention to write mu and nu in the same expression when they look the same and sound the same. It's just the notation most textbooks use. I'm sorry, if I were making textbooks, I wouldn't make two symbols that look the same and sound the same. But well, that's life, right? So yeah, we have these relations here. Now there are two ways to go about this. We can declare that these gamma numbers are just matrices, right? And the matrices that they'd have to be are the Dirac gamma matrices that we see over here. Just copy pasta that one. Move it along down a bit more further. So yeah, we can declare these to be matrices like the complex numbers, or we can take the alternative route and declare gamma naught, gamma 1, gamma 2, gamma 3 to be their own new numbers, their new cool numbers, like I. And we can just do this. So when we say that these gamma numbers are matrices, that's only the matrix representation. But we could also treat these as their own numbers themselves, as we do with the imaginary numbers, square root of -1. So when we treat them as their own numbers, we have the relation. You have these relations over here, right? So cool. So if we multiply these gamma numbers, we get like scalars as a result. You don't get like matrices or vectors. We just get pure scalars. Now, these gamma numbers. I'm gonna call them gamma numbers now. These gamma numbers, you can add them, right? You can add them to each other. You can even subtract them. They're linear under like multiplication, right? You can do like these vectorish things to them, and it makes logical sense. So we said that these gamma numbers, at least gamma naught, gamma 1, gamma 2, gamma 3, they serve as a basis for a vector space. So gamma mu is an element of this vector space. Now there's of course more caveats to the definition of a vector space, but basically, if you can add it, if you can subtract it, if you can multiply it, it's a vector space. So yeah, these gamma numbers form a vector space. Okay. So, and the gamma numbers are elements of the vector space. So, what's also cool here is that when we multiply these gamma elements together, we get scalars. So these gamma numbers are bilinear forms. Because remember, a bilinear form by definition is just some function that maps a vector to a scalar. And these gamma numbers, when multiplied by another gamma number, actually gives you a scalar. So these gamma numbers are bilinear forms. So these gamma numbers are they form a vector space that is equipped with a bilinear product slash form, right? So we see that this vector space is an algebra. Now I'm not talking about the field algebra, like the like that you learned in 8th grade. I'm talking about algebras over fields, which makes no sense, but poor choice of words. But the algebra that we're dealing with isn't the algebra that like y equals mx plus b. We're talking about algebra structures in math, and an algebra is defined as a vector space that has a bilinear form to it. And since these gamma numbers constitute a vector space that has a bilinear form defined on it, these gamma numbers, the vector space of these gamma numbers, are an algebra. So the vector space of these gamma numbers are an algebra. And the specific name for this algebra is, drumroll, the Spacetime Algebra. That's what it's called, the Spacetime Algebra. The Spacetime Algebra, if you go back to our definition at the start, it's just the vector space with the binary product with the basis gamma naught, gamma 1, gamma 2, gamma 3, or gamma mu, or the gamma numbers. Now, yeah, they're numbers now. So yeah, that's what the Spacetime Algebra is, and we're going to denote the Spacetime Algebra as the symbol H. So these gamma numbers are elements of the Spacetime Algebra H. Okay, the Spacetime Algebra is just the algebra of the gamma numbers. Now, the particular type of now there are types of algebras in math. There are various types of algebras, and the specific algebra that the Spacetime Algebra is a Clifford algebra. Now, this is a whole new topic on its own. I'm going to cover very, very briefly, but the Clifford algebra, CLAB, it's just an algebra where some elements square to -1 and some elements square to +1. This is a very, very oversimplified notion of the Clifford algebra, but just to put it very briefly, that's what it is. So, where A is just the number of elements that square to 1, and B is just the number of elements that square to -1. Okay? Now, the complex numbers, for example, would be a member of the Clifford algebra of 2, 2. Since I squares to -1, minus I squares to -1, 1 squares to 1, and -1 squares to 1. So 2 elements square to +1, 2 elements square to -1, so it's Clifford algebra 2, 2. Now, for our gamma numbers, you have like gamma naught squares to 1, and then gamma 1 equals gamma 2, gamma you know what I mean, right? These square to -1, right? So 1 element squares to +1, and 3 elements square to -1. So we said the Spacetime Algebra is a member of the Clifford algebra 1, 3. Since 1 element squares to +1, 3 elements square to -1. In the end, it's instant algebra. So, and these gamma numbers are members of the Spacetime Algebra. So yeah, that's the Spacetime Algebra. There's way more to Spacetime Algebra. This is actually a topic called the Geometric Algebra, which we'll be exploring more in the latter future videos. I'll be making more parts to this Spacetime Algebra series. We'll cover we'll cover the wedge product and quaternions, bivectors, pseudoscalars, all that cool stuff, but in future videos. I just wanted to give you guys a taste. I just wanted to give you guys a taste of this Spacetime Algebra in this video. So yeah, I hope that you guys like that video. I've been preparing for it for a very long time. So please share it if you guys liked it. And yeah, have a